All right, so we're going to talk about something called aqueous reactions today. Okay, and the thing about aqueous reactions and the reasons that we need to know about them is because 98% of our planet is covered in water, and lots and lots and lots of chemistry happens inside water. And so that's where we're working, and that's what we're going to start with today. Okay, so anytime that you have any reaction that happens in water is known as aqueous. And so, just so you know, and if you see it written like that, a little AQ in the bottom of it, that means that that's in your solution. That means that that is dissolved in water and it is an aqueous solution. Okay? And so that brings up another set of phrases that I want you to know. Solution. All right, and so a solution in our demonstration, in our definition, is going to be a homogeneous mixture made up of two or more substances. And so that's a pretty easy definition for us to use. But that's what we're going to look for and what we're going to use. And so a aqueous solution is going to be made up of water, but any solution is a homogeneous mixture made up of two or more substances. We can have solid homogeneous or solid solutions, like a brass alloy is a solid solution. You've got copper and zinc together, and so that's another definition. Okay, a solution is made up of pieces. It's made up of a solvent, and it's made up of a solute. Okay, so a solvent is the substance that is present in the greatest quantity in the solution. And so whatever you have the most of that makes up that solution is going to be your solvent. So that's that. The other one, the solute, what else do we want to talk about here with a solvent? With a solvent, we want to say that this is what does the dissolving. So usually does the dissolving. And yeah, most often it's going to be water, because that just makes the most sense. And that's the kind of planet we live on. It's got water in it. So that's where that's going to be. The other one, this is the solute. This is the part of a solution that is in the lesser quantity. Okay, so this is what we have less of in terms of the pieces, the parts, and all of that stuff. Okay. The solute gets dissolved by the solvent. Okay, later on we're going to talk about how that happens and how those pieces do all of that stuff, and we'll get into that when we get back to it. So, all right, that's the first part of this. So we're going to jump into something else in just a little bit. All right, so now if we're going to talk about a solution, a good example of that is salt water. And so if we have a saltwater solution, so water, H2O, that's your solvent. And so that's the one that does the dissolving. All right, and then in this case, NaCl, or salt, table salt in this case, is your solute. Okay, and so the water is going to be the higher concentration, or the higher percentage of that solution, the higher percentage of the mixture, and that's just kind of how that works. Okay, now we can break solutions up into two different types as well, and so solutions can be broken into electrolytes. Spelling. Into electrolytes and non-electrolytes. Okay, now you have all heard the phrase electrolyte. It's all written on your bottle of Powerade or Gatorade or whatever it is that you're consuming. And so, but what does that really mean? Okay, and so when we talk about it, an electrolytic solution, or a solution that has electrolytes in it, is going to have stuff. So electrolytes are solutions that contain ions. Okay, and so what that means is this is going to be something that has broken apart, and those ions are able to float around inside solution. And because those ions can float around free inside that solution, that means that electrolytic solutions, or solutions that are electrolytes, can conduct electricity. This is a pretty common test. In my previous classes, you guys have seen electrolytic testers or conductivity meters, and we check for that all the time. And so that's something that we do pretty commonly. And so electrolytic solutions are broken up into weak and strong electrolytes. So weak or strong. Okay, and so a weak electrolytic solution is a solution that conducts a little bit of electricity and a strong electrolytic solution conducts electricity very well. And the reason for that is this different fact depends on how much stuff is in solution, on how many ions are in solution. Okay, so a strong electrolytic solution is going to have lots of ions in it that are free to move around inside that solution and carry a charge, whereas a weak electrolytic solution has fewer ions in it. And so that means it doesn't have enough parts in it to actually carry as much charge. And so that's how we would break that down. All right, we'll be back. Now, all of this brings up the question, how do compounds actually dissolve in water? And so that is a focus of conversation that we need to have here. Okay, and so here we go. How do we actually dissolve compounds in water? So first of all, let's look back at some of the stuff we've talked about previously. Okay, let's talk about a water molecule. Your friend and mine, water. Okay, so there's a water molecule. If you remember, we've got two lone pairs of electrons floating off of that. If we were to look up the difference of electronegativity between an oxygen atom and a hydrogen atom, we would see that these are what we call polar bonds. And so what that means is that all the electrical density in these bonds spends their time around the oxygen atom. Okay, and so we could write it with the little dipole arrow, showing that this end becomes slightly positive of that bond and this end becomes slightly negative. Or if you remember correctly, or if you remember not correctly, we could use Greek lowercase letter deltas, okay, to show that one end of this is positive and one end of this is negative. So this is our positive side, this is our negative side. And so what that does is, because water molecules are polar, that changes their properties a bunch. Remember, water has a really high boiling point based on its mass. Compared to other compounds like it in its weight class, it actually has a really high boiling point, which is kind of cool because that's one of the reasons that life exists on our planet. And so, but because of this factor, water molecules are attracted to ions. Okay, and so because of this, because of polarity, water is attracted to ions. All right, and so it is that attraction that causes things to dissolve in water. Okay, and so what happens is, if we take sodium and chlorine, okay, sodium and chlorine, so we take NaCl And when NaCl hits water, it breaks apart into an Na plus ion and a Cl minus ion. Okay? And we would say that this is aqueous if we were to write it that way. Okay? Now, imagine, if you will, that you have a sodium ion chilling here and a chlorine ion chilling here. Okay? And so let's say that we were to take, and we'll use this color because it looks cool. Okay? So imagine a bunch of water molecules here. We've got one side of this oxygen, of this water molecule, this oxygen part, has got a negative charge. And so that negative piece is going to be aligning itself, or trying to be attracted to this portion of this sodium ion where that ion sits. And you can see that it would happen in more than just one spot. It's going to be over here, and it's going to be over here, and it's going to be over here too. Okay? And so this cation, the positively charged sodium in the middle, is going to be attracted to the oxygen atoms in the water molecule. And so we end up with a bunch of different water molecules stuck around it to the outside. And they're not really stuck, but they're attracted to it. Now, this is a two-dimensional representation, and so this is just a flat surface. But you could imagine that this would happen in 3 dimensions, wrapped all the way around that sodium atom. Now, the same thing happens with our water, with our chlorine, our chloride ion as well. And so if we take, I'll do a different color because, why not? If we take the other side of our water molecule, our positive side, you're going to see a little bit of a hydrogen kind of wanting to stick to that chloride ion. And so we can see here's another hydrogen that would be sticking to it. Oxygen, hydrogen, and we'll put another one here. Okay? Okay, now, and so these are temporary, I guess, attractions that are there and that hold those two together. And what this does is, again, you can see this wrapped around in 3 dimensions. You can see this sticking out in the front and out the back of this thing, and you could see that it would have kind of this ball of water molecules stuck to this ion. Well, this is called the solvation shell. Okay, and all that means is that you have water molecules sticking to ions. Wrong 2, I guess. Sticking to ions. And it is that sticking to ions that makes things dissolve. It is water molecules' positive side and negative side that makes cations stick to something, or anions over in this case, and that is why we get dissolving of in solutions. So that is the round, or the short, the long and the short of it, really. So, all right, hang on, we'll be right back. Okay, so now we got one more aspect of this that I want to talk about before I'm going to stop this video. So we're to the point where I need to stop it anyway, but I got a little bit more. And so when we talked about weak electrolytes and strong electrolytes, we talked about how things mean that there's fewer ions in solution. Okay, and so that gives rise to something that we're going to talk about called chemical equilibrium. And we've seen this before, but we're going to talk about it again here. Wowzers, Batman. Okay, chemical equilibrium. Okay, so vinegar. CH3COOH in aqueous solution. Now when we talk about vinegar, and you guys saw this last year in class, where we have double-headed arrows, this breaks apart into CH3COO minus in the aqueous phase plus H plus in the aqueous phase. Okay? These fancy double-headed arrows, this means equilibrium. And all equilibrium means, really, is that at any given moment, we have acetic acid changing to the products, and at that same given moment, we have these products reacting back together again to make acetic acid again. And so that's why the double-headed arrow. The arrow on the top pointing that way tells me that this is breaking up to make this stuff. The arrow on the bottom pointing that way tells me that this stuff is joining back together again to make that. And so what's really happening to each other, and This is a chemical equilibrium. And so what's really happening, though, is that the relative numbers of the pieces on both sides of the equation is remaining constant. Okay, and because of this remaining constant, this is talking about, or this is showing us to, or pointing us to, a weak electrolyte. So a weak electrolyte solution will be in equilibrium, whereas a strong electrolyte solution will not be in equilibrium. Okay, so if I were going to draw this one, let's say I drew hydrochloric acid, and if I wrote that as aqueous, that's fine. But hydrochloric acid is a strong electrolyte. It's also a strong acid, and so that means that it's going to break apart completely into those pieces. And so there is no double-headed arrow. There is no equilibrium present. All of this stuff, HCl, is all turning into that product. Okay, and so this is how we would write for a strong electrolyte solution, because there is no product returning back to reactant. So that's what's going on with that. Okay, and so with that, there we go. Thank you for your time. See ya.